Let's talk about how not to build an SLO platform. My name's Alex Nauda. I'm CTO at Nobl9. Nobl9 is an SLO platform. We calculate service level objectives based on service level indicators pulled from our customers' existing metric systems. I'm going to talk a little bit about what Nobl9 is and why we chose to use InfluxDB as a core component in the first place. I'll touch on some features of Nobl9 that are supported by InfluxDB and show you how they work at a high level. And I'll touch upon some lessons learned and some challenges we have going forward that I think may be of interest. So Nobl9 is an SLO calculation platform that, like I said, sits on top of our customers' existing metric systems. We support a wide variety, 15 to date metric systems. We pull in SLIs from those systems, calculate SLOs from them, and then we present that to users in our web application and also in our command line interface. Here's a high-level black box view of our architecture. On the upper right, the blue shaded part you can see represents Nobl9. And I know this is maybe painfully high level, but stick with me here. You can see we sit on top of those existing metric systems. We pull in this very narrow amount of data, an SLI, which usually consists of a query against an APM, a metrics data store, a logging system, a log aggregation system, etc. We perform calculations on those to derive SLOs. And at a high level, an SLO, once it's calculated, consists of a collection of time series, things like your error budget, your burn rate, etc. And we store those in everyone's favorite time series database, InfluxDB. We also have a configuration module based on our API. And our users can configure Nobl9 through our web application and also through YAML. So we're doing SLOs as code, and we have a schema that can be used to define these SLOs and feeds into our API. And then we present those SLOs in a variety of ways in the web application and also through notifications, data exports, lots of graphs and reports. And I'll give you some examples and I'll show you where InfluxDB fits into all of this stuff. But first, why did we consider using InfluxDB in the first place? So SLOs, like I said, are essentially time series data at the end of the day. And we were looking into time series databases. One of the things that's really important in our application is for our time series database to be very query friendly. We need a lot of flexibility to make the kind of charts and graphs that we do and the features that we do. I'll show you some, and I'll go into some details about how they're built. Second, we offer Nobl9 as a SaaS product, and we host that on Influx Cloud. It's on Influx Cloud 2.0. But some of our customers don't want to use a SaaS platform for maybe security or compliance reasons or privacy reasons. So one of the nice things about Influx is that it offers an enterprise solution. So our customers can self-host it and self-manage it. Many of them are Influx customers already. And then we also have the open source version that we can use in our development environments. And there's good query compatibility across them all. And third, we were looking for commercial support. It's definitely a firm requirement for us just to manage our SaaS platform, especially when we were just starting out and we had a really tiny team. But that's also helpful to our customers in a couple of ways. One is if we embed InfluxDB into our product, we may need commercial support in order to support a customer who's running that themselves. And in addition, because it has commercial support, it's widely adopted among enterprise companies. They may already have an existing contract with Influx and host it on an existing InfluxDB. And so in those three different ways, InfluxDB was a good fit for us, and we launched into building building an SLO platform based partly on InfluxDB. At a high level, here are some of the features of Nobl9 where we found InfluxDB to be particularly useful. The first is in our data intake. So we receive telemetry data from these metrics data sources, and I'll go into detail about part of what our architecture looks like, how we got to that architecture, and why. Next, we have this calculation pipeline where we're processing that telemetry data and we're doing some math. The math isn't particularly high level in terms of the education you might need to do it. However, dealing with sampling artifacts and data anomalies and all those different things can be quite difficult in practice. And, we learned that the hard way as we went along. Third, we have our graphs and reports, and this is really a core component. InfluxDB underlies that entire subsystem. We have a variety of visualizations, real-time views, historical views. I'll give you some samples. Next, we do alerting on those SLO time series. We have a variety of integrations there. It's all based on configuration, like I said, in YAML, from the GUI. And then we also have data export. And there's at a high level, there's two types of data export that we need to support. The one is a real-time data export. In other words, hey, I like your web app, but I'd like to see it in my visualization, in my dashboards alongside my other stuff. And also, we offer batch exports to other tools, such as Data Lake, Data Warehouse. We have a Snowflake integration. We can export delimited files to cloud object storage or file system. So let's talk first about the data intake and the telemetry requirements. We support a wide variety of sources. Like I said, 15 and counting. We're adding maybe 2 or 3 a month. And they span a variety of different types of systems: metrics, APM, real user monitoring, cloud platform built-in metrics like AWS CloudWatch or Azure Monitor, etc. Log aggregation systems like Splunk, also Elk. So we have an Elastic integration, synthetics in a bunch of commercial products, and potentially also taking in data from data warehouses, because sometimes you want to tie an SLO to a business metric, some kind of KPI. And so we have some requirement to pull in from this wide variety of sources. We also need to integrate in 2 ways. One is via agent. Some of these, even in our SaaS system, some customers would like to connect to our SaaS system from behind their firewall to a metric system that resides behind their firewall on some private network. And we offer that via this agent, which is, you can think of as sort of like a self-hosted sidecar container, as well as a direct connection, a SaaS to SaaS connection. So if you are using Datadog or New Relic, or even just metrics from your cloud provider, from CloudWatch or Azure Monitor, we can, and if you're using Nobl9 SaaS, we can connect over the internet if you're willing to provide us the credentials. And then we adapt to a wide variety of different paradigms. Some of these are API calls, some of them are queries, sometimes there's push, sometimes there's pull, there's these authentication mechanisms. It gets pretty complex. We need to be robust to the types of issues that typically are going to come up in a high number of connections type of environment. We need to conform to these security models that are fairly well understood, but they're not trivial. And then we run all this through configuration, as I mentioned. So when you look at our architecture here, we're supporting so many of these data sources. You can see InfluxDB coming soon. It's in development now. We needed a way to connect to these, including sometimes custom ones. Sometimes we have a customer who wants something they completely built in-house that they'd like to connect to. What our architecture looks like when we're connecting either via the agent or directly is a little bit different, but it has some commonalities to it. The agent has to run easily in our customer's environment in their Kubernetes or some Docker environment. And then in our direct service connecting SaaS to SaaS, we need to be able to run similar componentry inside our application, whether we host it or whether a customer hosts it themselves in their own cloud account, or even eventually in a data center. When you create a connection, an integration to one of these, we're going to present you with, hey, here's how to run this this is a Kubernetes deployment. It's a lightweight agent, and you can also run it in Docker. Also, I mentioned that we configure these via GUI or via YAML, and this can get somewhat complex, but the way that we decided to build this at the end of the day is that we started with Telegraph. Telegraph is just an extremely flexible, very widely adopted sort of Swiss Army knife for data pipelining. We had to significantly extend it. We have all of those integrations I mentioned involve the vast majority of them involve a proprietary input plugin. We have proprietary output plugins to feed to our own APIs as opposed to dropping it directly into Influx. So we did have to extend it significantly, but Telegraph makes a really good backbone for this agent. And because it's widely adopted, many of our customers are already familiar with it. So, getting them to a point of comfort where they're able to run this thing and manage it within their own infrastructure is a lot easier when it's something that's already understood. It might have already been vetted by their security team or architecture team. Some of the other stuff we had to add to it is, as I mentioned, we had to develop our own input and output plugins. We send data to our data intake REST API, and then also we send configuration down to the agent from that REST API, and we dynamically reload that configuration. So we had to get into the guts of Telegraph a little bit, but it's been a really successful project to do so far. The direct connection SaaS to SaaS is a little bit different. I'm not going to go into too many details there, but Telegraph is still a component of it, and we have shared code including Telegraph across both the agent-based and direct architecture. That's really working out well for us. Let's talk about calculation. So basically, we're receiving this data into our intake API. In our original design, we weren't doing it that way. I think a lot of in-house built SLO systems leverage a central database system, often a time series database or some other database, in order to perform most of the calculations. And we found we hit a ceiling with that pretty quick. And what we're doing for our calculation varied from that. The base requirements are that we need to calculate up to the minute SLOs as the data arrives. We really want to show it, show an auto refresh moving chart as data arrives. And we needed to support some flexibility in our SLO features. So for example, in order to really address not just the most common SLO use cases, but to really have a good fit to a lot of different business situations and technical situations, you need to support a bunch of SLO features. Some of them that we found are rolling windows versus calendar aligned windows. Rolling windows are really good for operational situations where your customer doesn't care what day of the week it is. They just want to, check out with their cart versus calendar aligned windows where maybe you have a particular SLO, maybe even on a technical metric that's supposed to map to some business metric, whether it's cost or revenue or something else that's reported on a calendar aligned basis, such as a calendar month or calendar quarter. We need to support that. Likewise, we want to support ratio metrics, which is your traditional SLO ratio of good events over total events or good minutes over bad minutes. As well, we wanted to support threshold metrics so that we could move, let's say, the configuration of the breaking points of a latency metric, where the latency becomes too slow. We wanted to move that into Nobl9 configuration, make it easier to manage and to change. And in order to do so, we had to move that into some custom code. And then we also found there's a significant difference between occurrences-based calculations or event-based SLOs versus time slice SLOs that really just count, is the minute good, is the minute bad, versus were these requests or attempts good, and were the requests or attempts bad. The original version of this we built completely in InfluxDB. And for us, this was a huge prototyping win at that time. This was pre-Flux. We built that on InfluxQL. We could have done it in Flux. The queries were really intense, and we could make it work, but we found that we would have to scale vertically, and calculating those SLOs repeatedly on the fly could be extremely intense and potentially costly. It would be a massive database. The calculations are really memory intensive. The longer the SLO time window is, the more it costs. So if you have an SLO that's supposed to run for a year time window, that would be a absolutely huge query, depending on your data granularity. Once you add in requirements for things like high availability, disaster recovery, we found that a vertically scaled database solution is really not ideal for this. And what we ended up on is, here's a little snapshot of an internal diagram. Re-architected this to custom code based on Kafka. So what we ended up with is a sort of FIFO calculation. It maintains state. It uses object storage as a backing store, so it can persist and restore state across relocations. But the advantage we get out of this is that it scales horizontally. We're still using InfluxDB and other databases for where they're really strong. And obviously, if our load gets really high, if our use really picks up in a single instance of Nobl9, we also have to scale those vertically. But we can scale our processing pipeline horizontally, and that we found is a huge advantage to both cost and stability. Next up, the query requirements. This is really where InfluxDB shines in my experience. We have a wide variety of visualizations. I'm about to show you some screenshots. We display both up-to-the-minute data that sort of changes dynamically as new data rolls in, as well as longer timescales, historical timescales. We keep the data over a year so you can go back. There's really no hard limit on retention except for practical limits and the cost of storing tons of historical data. We allow users to seek through the data with a time selector, and we can support a multitude of SLOs running at once and then chart them all. Chart them all in this variety of ways. So let me show you some of the ways we do it. This is what we call SLO detail view. We have a chart of the incoming SLI data, and because we're zoomed to current time window on this SLO, which happens to be a 30-day SLO, the granularity of this, each point on this chart actually contains multiple data points. And so we percentile that for you. You can see the reliability burn down, which is your actual SLO value. You can see that we started this particular 30-day window where our SLO was almost blown at 99%, which is the target for this SLO. And we had some untoward events that brought us even lower. And you can see that anytime that there's a spike up here that crosses that threshold line, the threshold that's configured in Nobl9, you're going to see a corresponding error budget burn down here. And you can see some of them, like this spike right here. This must have been an actual outage. You'll see a longer period of burn down here where we actually lost a significant amount of reliability right in that particular event. All of this is built out of InfluxDB queries. I'll get to some of the tricks we found, or in particular what we had to do to make that happen. But if you want to go into real details, I'd also love to chat with anyone who's dealing with this kind of scenario. You can hit me up online, offline. It's a constant invention and constant architecture question for us as we design new visualizations. So this is our grid view. On this view, we display a multitude of SLOs and thresholds within an SLO, which really are separate objectives. We display them all side by side and allow you to sort of see at a glance how you're doing. This one looks like we're all in the green, but as you can see, there's been some burn. This is using a rolling window, so we actually can also recover error budget as bad behavior sort of falls off the back of the window. This one is just similar to the reliability burn down chart here, is what we're displaying there. We also have some summary calculations. This is a historical report where we show over an arbitrary time period. I just set it up for a month here, but we show over an arbitrary time period, even stretching back, like I said, at least a year or more. You can see how a variety of your systems have performed. This is sometimes useful for weekly or monthly check-ins, or maybe even a quarterly road mapping where you're sort of deciding across your portfolio where do you want to invest in reliability. Maybe decide we need to shore up this system because we can't sunset it yet, or hey, it's really time to sunset that, where's the replacement coming along, and make those kind of decisions as well. And we also offer this service health dashboard, and this is a summary view. This is actually at the service level, so you can see there's a service here, and when I took the screenshot I clicked on there, and you can see the SLOs that are within it. There's 3 active SLOs in it. 2 of them have blown their budget. 1 of them is still healthy. And this is it's useful for a variety of use cases, one of which though is more of an executive view or a manager's view across multiple services and systems to see how I'm doing at any given point in time. We also have a lot of display options for this, but again, all of this stuff queried out of InfluxDB. It's all in Flux. We originally built a lot of this stuff in InfluxQL, but we moved it all to Flux. And the flexibility we found is really sufficient for this wide variety of creative use cases. I feel like there's certainly work involved in creating these things, but InfluxDB is a real asset for us in rolling new features, new visualizations, or modifying what we already have as we find issues or feature requests with it. The data granularity or the resolution of that data can be challenging just due to the sheer cardinality in those queries. So one of the things we do is we downsample. We don't downsample and throw away the data. We downsample and we keep the more granular data as well. But we do need to downsample, and sometimes we'll choose to use the downsampled data for display depending on the length of the window and what's being displayed on the screen. And we do that with InfluxDB tasks in Cloud 2.0. This particular kind of operation does require some consideration with compatibility across code bases of InfluxDB because it works a little differently in the other systems. They're all capable of it though. We're optimistic that given the compatibility work that the InfluxDB development product teams have done in getting really good compatibility on the query side, we're optimistic that that might get even easier across those code bases as well. Let's talk alerting. We considered a variety of different approaches to alerting. One of our main features here is we're just alerting on those time series data. So we're alerting on burn rate condition or error budget being exhausted or partly exhausted or some amount of your error budget being burned. And we support a really wide variety of alert methods and destinations. And you can see here's the ones we're currently supporting here. There's also a really rich custom webhook in there. And because of both the sort of unique nature or SLO-specific nature of the alert conditions, as well as this variety of integrations we support, and we'll be adding more to that as well, we decided on this one we should go with something on the custom side. And we did this in mostly custom Go code hanging off the same Kafka. So I would say the big driver to that architectural decision was that alert method integration, really, because we have to integrate with so many different APIs, webhooks. It's very tool specific, and sometimes the way we have to react to that and the sort of error handling we have to do is just really, to present those errors back to the user if there's some configuration problem. It was really easier to do that in custom code. And one example of that is this custom webhook that I mentioned, where you can even put in custom headers and optionally encrypt those and customize your request body to the webhook to really integrate with anything, including like CI/CD systems or even custom systems that our customers use. They can usually hit all of that from our webhook customization. So I'm glad we went in our particular case with a very custom version for alert integrations, but I can imagine that if our surface were much more constrained in terms of what we had to support here, then we very well could have gone with we could have gone with something much more stock. But I feel like we made the right decision given what we're trying to support. Data export. So what's the point of calculating all these SLOs if you're just going to lock them up, even inside of InfluxDB, but have them locked up inside our system? These SLOs need to be shared to a variety of places, and there's really two categories for this. The one is a batch data export. We export delimited files to, as I mentioned, object storage or to file systems, and then we have specific tooling for Snowflake import and for BigQuery. And that's completely separate from a real-time data export. Use case for real-time data export is that usually customers want to display SLO time series alongside their other metrics, and they're already using some other dashboard or some other visualization, and they want the data to appear there or trickle in or have a real-time incremental export integration. We decided that the batch piece of this should be custom. We have to manage authentication within clouds, across hosting, and that was kind of a wrinkle. We have to manage the timing and performance of that, and we have to integrate with whatever preferred query system they're using. Like I said, we're supporting a couple of the popular data warehousing or query systems now, but we're looking to add more later. But the real-time requirements are interesting and different. For self-hosted customers, Influx, again, is a huge asset to this, because if they have a dedicated InfluxDB inside of Nobl9, and let's say they're running in their own data center, they can just use Chronograph, or they can wire up InfluxDB to something else if they want, because InfluxDB has great integrations to a variety of tools. For SaaS customers, it's a little more challenging because our InfluxDB in our multi-tenant SaaS system is multi-tenant. We can't just allow people to connect directly to that InfluxDB. It's under production controls. So we're developing a real-time data feed now, and we'll support popular destinations, for example, and send it to another InfluxDB, and integrate the same way to your heart's content is what we're thinking to address that part. I want to mention one key challenge that comes up, and that I'm expecting will exacerbate as time goes on, and that is what I've nicknamed faceted SLOs. I don't think this is in the original SLO literature, although you might find a similar technique maybe in windowed user uptime white paper or something like that, but it's a pretty simple use case to explain. We want to create a single global SLO on a given SLI, but provide the ability to drill down. And especially when I'm talking to B2C companies, but actually any company may have this situation. They'd like to have a single global SLO, and if it is consuming some error budget, or a little more error budget than they expected, they'd like to drill into that and break that down. An obvious one might be, I want to see this by region of my cloud provider, or by data center if I'm hosted in multiple data centers. I might want to slice it by customer. Show me which customers are suffering, or which of them have hit this, which even tried to use the system during this SLO, during this error budget burn event. They might drill all the way down to an individual user, especially depending on the nature of their business. They might also want to break it down by feature or user journey. Present me with an SLO of, basically all of the usage of my web application, but then drill in by component so I can see feature by feature which ones were most impacted. They also drill by aspects of their infrastructure or internet infrastructure, like the geographic location of the users or connections, client platform inversion, similar to any web tracking tool or client side tracking tool. Break it up by network. Let's say slice it by ASN. Slice it by some aspect of their infrastructure, like availability zone or subnet, some aspect of their hosting. And the main issue that comes up here is that the cardinality of this data gets really high. It looks more like observability platform data than a simple SLO. And we might consider a columnar database for this, or other similar data stores. Not that I'm looking to sort of rebuild every observability tool out there. We're really focused on SLOs. But one option that I'm watching closely now is IOX. We understand that the cardinality limits could really be raised by that. It's one of these things where we want to watch it and see if it could potentially meet our needs. And like I said, we've had great experiences building on Influx so far, and we're hoping to take that forward, and we're really hoping that this could open up this new set of use cases for us. Thanks a lot for listening. Again, my name's Alex Nauda. Hit me up online. Reach out if you would like to learn more, or if you want to just talk about some of the topics that I described here.